Today we're going to talk about normal subgroups, and I want to start by asking a question and giving you a reminder. Let's start with the reminder. The reminder is about the way that we multiply sets. We're multiply together two cosets. So if I have two cosets, left cosets by default, let's say GS and HS, where G and H are elements of a group G, and S is a subgroup of the group G, then the way that I multiply these two sets together, I do GS times HS, I get a new set. And that set is the set of things, let's say XY, where X is in the coset GS, and Y is in the coset HS. And so what that really means is that I've got something that looks like, I'll say GX prime, HY prime, where X prime is in S and Y prime is in S. So this is how we multiply sets together. We basically take all the possible elements in GS, multiply those by all the possible elements in HS, and we get this new set. And our question that we're going to handle today is, when is GS times HS a left coset of S in G? Another way of phrasing this question is, when is coset multiplication closed? Which is to say, there exists some element, let's see, we use GH, let's say K in G, such that GS times HS is another left coset, and it's the left coset KS. And that's the question we're going to answer today with normal subgroups, right? We're going to figure out, when do we multiply two cosets and get another coset? All right, moving ahead to some definitions in the Redfield notes. The first example in the notes starts getting into this question. It's looking at a subgroup of S3, and we figure out the left cosets of that subgroup, and we do some multiplication, and we don't get a coset back. We know that this element that we got through this multiplication right here can't be a coset because it's got too many elements, right? All our cosets are supposed to be the same size by proposition 20.4. We started with a subgroup of size 2, and we got 4 elements out when we did this product. So not a coset. But in the next example, we find that we do have a coset. And there's something special about the subgroup H that makes this happen. So let's look at the next proposition. All right, so proposition 23.1 says that if we've got a subgroup H of a group G, the following things are equivalent. So item number 1 right here says that for all x, y, and g, there's an element g and g, so that if we take the cosets xh and yh and multiply them, or do the group operation that's passed down to the cosets, we get another coset. So property 1 is saying that coset multiplication is closed. When we multiply two cosets, we get another left coset. Number 2 is saying that, in fact, the coset that we get is given by taking the representatives, x and y, and multiplying them together. So it says a little bit more than it is a coset, but actually which coset we get. So which coset we get when we multiply these cosets. So if there is a coset that I get when I multiply xh and yh, that's true if and only if that coset is actually xyh. So it's saying exactly which element in the group G we can take to be the representative. Now, part 3 is pretty useful. Part 3 is saying that if we think about a set of this form, and we'll talk about that more in a minute, so we take an element x in G. If we look at this set x, h, x inverse, which is going to look like x times h times x inverse, where little h is an element of our subgroup H, every element of that set belongs to the subgroup H that we're working with in our group G. And that's actually equivalent to these two sets being equal, and that's kind of a fun one to show. So this says that actually in part 3, that inclusion, we could have made an equality. And you can sort of imagine this by saying, if this is true, then it's also true that x inverse x h x inverse with an x on the other side is going to be contained in x inverse h x. But of course, when we put those x inverses and x's together up there, we get just an h again. So this guy is just h. So h is equal to that thing. And since 3 and 4 were true for all x and g, it doesn't really matter whether we've got x inverse on one side or the other. And so now we've sort of got h sandwiched between these two things. So that's where the equality comes from. And part 5 is saying, oh, actually, we could think about the left cosets being the same as the right cosets. So if I take x from my group G, the left coset, xh, is the same as the right coset, hx. And you can kind of imagine that from coming directly from 4 by saying, oh, well, if xh, x inverse is equal to h, if I multiply on the right by x, I'm going to get xh equals hx. So all 5 of these things are equivalent to one another, and there are 2 of these that are really useful when we're working out examples later on. I'm going to star them. It's number 3 and number 5. I like both of these for working out examples, and I'll say a little bit more about why that is later. But think about 3 and 5 as being sort of important for doing anything with calculations or computations. And again, I'll say more about that later, but those are really the ones that when we get into working out examples, they're going to be really useful for us. Here we get to the definition of a normal subgroup. If any of the properties in 23.1 hold, we call the subgroup H normal. Usually, to check that something's normal, the easiest part to use is part 3, and you'll see that right here, right? That xn, x inverse contained in n. We only have to check one containment, and that's often not too bad to do in proofs and in computations. So we say n is normal if n is a subgroup of G and xn, x inverse is contained in n for all x and g. We also have a special notation that we use for this. It's kind of cute, I think. We say n and then a little triangle in G, and I will remind you how to check that as soon as I remember how to check that. But you'll see this. Sometimes you'll see it with a bar below. So it's really just like you took the subgroup symbol and you closed off one end and turned it into a triangle. And that's how we indicate that something is normal, that a subgroup is normal in the group G. So if we want to check that n is normal, we want to check that it's a subgroup, right? And that's what this next note says. So we check that n is non-empty. We check that n is closed under multiplication or the group operation. We check that inverses belong to n, and then we check that n is normal. So the first 3 here, we check that it's a subgroup. And then this last guy that we're seeing here checks that it's a normal subgroup. If we're working with a finite group, we can sort of make life a little bit easier. We don't need to worry about inverses, right? That's what proposition 18.7 said. So if G and N are finite, we check that n is non-empty and closed under multiplication to check that it's a subgroup, and then we also check that xn x inverse is contained in n. So here's normal. Now, abelian groups are pretty awesome because if we have a subgroup of an abelian group, it's going to automatically be normal. And the way that we check that, you'll see, is by checking that xn is nx, that left and right cosets are the same thing. And so if G is an abelian group, let's just do a quick sanity check that that makes sense. If I take xn, that's the set of things that look like x times little n, where n is an element of big N, but my group is abelian, so that also looks like nx, where n is an n, and that's exactly what I mean by the right coset, big Nx. So that's where we get to use abelian. That's a pretty nice thing. But a group doesn't have to be abelian for its subgroups to be normal. I'm going to leave this next proposition for you to take a look at over here. This guy is a kind of nice one. Back in the day, way back before the wildness of the semester started, we looked at what happens when we've got a ring homomorphism. So I've got a ring homomorphism phi from R to S. Remember that it preserves algebra, so it preserves addition and multiplication. And I looked at the kernel of my ring homomorphism, which is all the stuff in R that phi sends to the 0 element of S. And we showed that this kernel was an ideal of the ring R. Right? Which means that it's a subring, but even better, it's a special subring that's closed under that like extra strong multiplication that pulls scalar multiples of ideal elements into the ideal. And so this next result is a kind of analogy to that. If I take a group and I look at phi from the group G to the group H, the kernel of that, so the kernel of this thing, which is everything in G that phi sends to the identity element of H, we can show that this is a subgroup, but even better, it's a normal subgroup. So we get that kernel of phi is a normal subgroup of G. So kernels, one of the themes of algebra is that kernels are pretty special elements, and I wanted to point that out here. And this is a nice proof to take a look at because it gives you a little bit of a reminder of how group homomorphisms and their properties work and how to check that something is normal. So why do we want normal subgroups anyway? Well, it's because if we've got a normal subgroup, then we can look at the set G mod n, which is the set of left cosets of this normal subgroup n in G. And the fact that this is normal means that multiplication of cosets is closed. So we're part of the way to, sorry, is not closets. Woo, it's that laundry analogy I used earlier, is closed. So we're part of the way to showing that G mod n, the set of left cosets, is actually itself a new group that we made by taking G and quote-unquote dividing out by this normal subgroup n. So that's right, that's our first group axiom, G1, multiplication of cosets is closed. So to show that it's a group, then what we need to check is that we've got G2. We want this to be, we want coset multiplication to be associative. And we can use proposition 23.1 to help us out with that. So if I take three cosets, let's say I have Gn times Hn Kn, proposition 23.1 part 2 said that this is really going to be the product Gn and then Hkn. And I can then make that GHK n, and my group multiplication itself is associative, so I can reassociate and make that GH times Kn, and now I can unravel this way. I get GHN times Kn, and that gives me Gn times Hn, Gn times Hn times Kn. Right, so I inherited associativity from the fact that the representation for a product of cosets is the product of the representative. So that's kind of nice. That was 23.1 part 2 that let me take this product and multiply the representatives together to get my new coset. Okay, so it's associative. I need an identity coset. So the identity coset is just the subgroup N. So if I take the subgroup N, that's the same coset as the identity of G times N. And now if I take, G times N, or Gn, the coset Gn, and multiply it by N, this gives me Gn times the coset En. And again, using 23.1 part 2, the new representative is just G times the identity, which gives me Gn. And similarly on the other side. So if I do N times the coset Gn, the same things happen, and I'm going to get that this is Gn again. So the identity for G mod N is the coset N that we modded out by. So the identity exists. And if I have, the last thing I need to check is axiom G4, which says that we should have, every coset should have an inverse coset that we multiply by to get the identity. So we need inverses. So if I take Gn and I want to know what its inverse is, I'm looking for something that I multiply by to get the identity times N, or just N. Well, I use the fact that in the group G, the element little g has inverse G inverse, and that tells me then that I can multiply those together and I get G inverse times N, which gives me the coset N. So we've got that coset multiplication is closed. If we multiply cosets, we get another coset back. And then we've got that the multiplication is associative, has an identity element, and every element, every coset in G mod N has an inverse coset that I can multiply by to get the identity element. And so this set, G mod N, when N is a normal subgroup, is called a quotient group of G mod N. And we call it a quotient because the notation looks like we're dividing, but also an example to keep in the back of your mind is if I take Z mod, let's say the subgroup generated by 3, so we've got, we'll call it 3Z, Z mod 3Z really comes out to be Z3, which is the set of, equivalence classes of remainders that we get when we multiply by 3. So we're relating this idea of cosets to division the way we did in the integers to get our groups, our rings of integers modulo some divisor, like in this case 3. So that's where the idea comes from. It's an extension of the idea of integers modulo something. In this case, we say it's a group modulo this normal subgroup, and we call it a quotient group. Now, one of the reasons that we like these quotient groups is that they're smaller than the group G that we're dealing with, and that's what proposition 23.8 tells us. The size of the group G mod N, where N is a normal subgroup, is the size of G divided by the size of N, and that comes from Lagrange's theorem. So Lagrange's theorem, remember, tells us that the size of the group G is the index of N in G times the size of N, right? And so this piece here is Lagrange's theorem. And the index of N in G is literally the number of elements in the set G mod N. So that helps us. This is like the good news here is that we take a big group, we find a normal subgroup, so let's call our big group G, our normal subgroup N, and then we make a new group, G mod N. It's a group, but it's a smaller group. And smaller groups are typically easier to work with. We know a little bit more about the structure of smaller groups in general. So in the next example, we've got S4, S4 is a group that has 4 factorial, or 24 elements in it. If our normal subgroup has 8 elements and we mod out by that, we've now ended up working in S3 mod n, which is a group with 3 elements, and there's a nice little corollary in chapter 21. I didn't mention it, but we'll probably use it again. If I have a group of prime order, then that group is abelian. So this tells me I started with S4, definitely a big non-abelian group. We can find lots of cycles that don't commute with each other. But when I mod out by this normal subgroup of 8 elements, I get a group of size 3, which is an abelian group. So somehow organizing our group into cosets and figuring out if those cosets form a group gives us a handle on the structure of the group, and it does it by sort of shifting our problem from the larger group to the smaller group, which might have nice properties, like, being abelian or something like that. So I will put up another video with some more examples of normal subgroup stuff, but this is your introduction to normal subgroups and quotient groups. I hope you are all doing well, and I will see you in office hours. If you have any questions, as usual, post them on Piazza. And hang in there, we're getting close to the end of the course.